Hi, everyone, and welcome back. It's Kira Garfolo again with Greenville Tech's Math 155. Today, we're going to start Unit 4 with geometry. We're going to talk about an introduction to geometry, kind of a review for things that we're going to be doing. We're going to talk about a lot of definitions, and we're going to start our discussion with angles. Welcome to Unit 4. Before we get started, this is the home stretch. There's only 4 units in our course, and you guys are starting Unit 4, so that's great. Most of this unit is based on geometry, and I know some of you have taken geometry in the past. We're not going to go too deep in some of these, but other things we're going to talk about in detail. We're going to talk about geometry as a whole, which is the study of shapes and all of their properties. Now, as I mentioned before we get into the kind of meat of this unit, we're going to have to review some basic terminology. For a lot of you, some of this will be review. Some of it is not going to be review, or perhaps it's going to be really old stuff that you maybe remember talking about but couldn't for the life of you answer on a test. So don't worry, we're going to start from scratch here. Let's start with some of the most basic pieces of geometry: points and lines. So a point we've already talked about way back in, was it Unit 2 that we talked a lot about graphing? A point just marks a position and it has no length and no width. It's just a single little point. We're going to represent it with a period and we're going to label it with a letter. So this right here is point A and the other one is point B. Now we can connect points with a line. And a line, formally speaking, is just a geometric object that is straight and it goes on forever. It's infinitely long. We're going to represent it drawing-wise by having 2 points on the line, and we're going to put that line through them like this one, okay? And then if we want to note it, if we're talking about, just referencing it in a problem, referencing it in an answer, we're going to write those 2 points and we're going to put this symbol above it, A and B with an arrow. So that's line AB, and it's the line that connects point A to point B. Now a line goes on forever and ever and ever, but if we want to just talk about a section of that line, then we can talk about a line segment. And a line segment starts with a point and ends with a point, okay? So here is line segment AB because it doesn't go on forever. It starts at A and it ends at B. If we want to note this, notice here we don't have the arrows before. Remember, as a line, we had this symbol above AB. But this segment does not have those arrows at the end of it. An array is kind of a combination of a segment and a line. It's kind of the way I think about it. It's going to be our building blocks for angles. Array is a portion of a line and it starts at a point and then it goes off forever in another direction. So it has one side that is finite and the other side that is infinite. We name it very similarly to a line or a line segment. We're going to still talk about 2 points, but we need to have the endpoint listed first and then any other point on the line second. So this would be ray AB. And notice that here, instead of having arrows on both ends, we only have an arrow on one end because it only goes off forever in that one end. Now, if we had point C here, it could still be AB, or it could be AC. It could not be BC unless we were talking about just this ray here, because we want to list where it starts first. Now, once we've talked about rays, we can talk about angles. And if we combine 2 rays starting at the same endpoint, we have created an angle. And that endpoint that's the same right here is called the vertex. Okay, so that is the vertex. You can think about it. Some of you that have taken physics, it's kind of the fulcrum. It's that bending point, okay? It's that axis where that angle is just going to revolve around. We can name angles several different ways. We want to take a point on one ray, and then the vertex, and then a point on the other ray. If we're going to name it that way, we always have 3 letters, and we always have the vertex in the middle. So this would be angle, this sign here, A, B, C. Okay. Now, if there's no ambiguity, so like here, this is the only angle we could physically be talking about with B as a vertex, You can also just have angle B, okay? Either of those will work as long as there's only one angle that could be referred to there as angle B. Now we've talked about the vertex in the sense of an angle, right? Vertex here forms that kind of bending point for the angle. But also all of our polygons or all of our shapes are made up of lines with vertices, I guess, in plural, okay? Different vertex points. So here in this triangle, this is a vertex because that's an angle. This is a vertex because that's an angle. And this is a vertex because that's an angle. Okay, so when we say vertex, we're talking about the same thing. We're still talking about a bending point for an angle, but the rays can kind of all get together and form a polygon. Now this, we could name angle. We want to talk about angle here. This could be BAC, or it could be angle CAB, depending which way we wanted to go, or it could be just angle A. Either of those would work. Now, we measure in this class angles in degrees, okay? There are 360 degrees in a complete revolution or a complete circle, okay? So we start here, and if we draw a counterclockwise circle and go all the way around, that's going to be 360 degrees. If you guys have heard, oh, he did a 360 or whatever, that means a complete turn. You start and you end in the same place. Now, a side note, some of you that have taken other math classes, if you've talked about trigonometry, if you've talked in physics possibly, radians are also a measure for angles, and we are not going to deal with that, okay? So if you Google something in this class and you start to see radians being discussed, you start to see measuring angles and things that involve pi, that's not what we're talking about. We're going to measure only in angles here. Now, there are special types of angles too that we can talk about. A straight angle is the simplest, and a straight angle is just a line. It measures 180 degrees because it's half of a circle, right? You can think about if you drew a circle around here, this is angle B, okay? You went half of a circle, so it's 180 degrees. Now we could name this one angle ABC or angle CBA, and really we could name it angle B. Now a right angle is half of that. A right angle measures 90 degrees. Most of you guys have worked in right angles before, even if it's just a matter of trying to hang something on a wall or make sure something's square. When you make sure something's square, you're talking about right angles. If we see this symbol right here, this means that our angle is a right angle. Unless you see that symbol, you really cannot count on it being a right angle. It may look really close, but maybe it's 89 degrees or 91 degrees. You really want to bank on seeing that little square symbol right there. Now we have straight angles, we have right angles. We also have acute and obtuse angles. So acute angle, you know, a cute little angle. I'm sure you guys have all seen the jokes float around. And that just means that it's less than 90 degrees. So remember that you have your right angle right here, okay? This does not extend all the way up there. So this particular angle is 45 degrees, so it is acute. Now obtuse is between 90 and 180. So that means we still have our right angle somewhere right here, and it's going to extend beyond that, okay? And here, maybe this is, I don't know, 110 degrees. Now, beyond just angles, we've talked about polygons, right? And we've talked about those vertices of angles can all kind of combine, all those rays, and they can touch other rays and they can build a shape or a polygon. So a polygon is just a closed figure made of those line segments that are connected at their endpoints. Each corner, just like an angle, is called a vertex. So point E is a vertex, point F is a vertex, and so on. Remember that plural of vertex is vertices. If you write vertexes, I'm not going to come after you. There are many, many, many special types of polygons, and we're going to talk about a lot of those today. A triangle is something that most of you guys are familiar with. A triangle is just a three-sided polygon. So look for a shape, look for three sides, okay? Three angles or three sides, triangle. Specifically, an isosceles triangle has two equal sides. So in this one, we have this one being equal and this one being equal, okay? And a lot of times we'll mark the equal sides like that. If we show a line, the ones that are marked with identical markings are equal length. An equilateral triangle, on the other hand, has three equal sides. So we sometimes see it marked like that. That means that all three sides have equal length. The next step from a triangle is a quadrilateral. And a quadrilateral is a four-sided polygon. You can think about quad being four. We're going to see lots of many special cases of these today too, and there are even more than what we talk about in this class. The first case we're going to discuss is a trapezoid. And a trapezoid is a quadrilateral, so it has four sides, and two of the opposite sides have to be parallel. Okay, the other sides are not. So in this side here and this side here, usually when we see those little arrows, it means they're parallel. This is a trapezoid. Obviously, line AD and BC are not parallel because they are going to intersect, but AB and DC are indeed parallel. So this is a trapezoid. We can also see a trapezoid being represented like this. Okay, that's also one, because you'd have these two lines as parallel, but the other two lines are obviously not parallel. Now, speaking of parallel, we can talk about parallelograms. And a parallelogram is just a four-sided, so quadrilateral, and all of the opposite sides are parallel to one another. Okay, so this is parallel to this. I'm going to put two here to mark that they're parallel to each other, but not the others. So AB and CD are going to be parallel, but AD and BC are not. Okay. Now, the opposite sides, due to some geometric things that we'll kind of touch on, but also just some mathematical theory, the sides opposite of each other are also equal length. Okay, so that means that AD is the same in length as BC, and then AB and BC are also equal length to one another. They do not have to be right angles. They do not have to be, equal sides. We're going to talk about a special case there in a second, but just know that across from each other, they are going to be equal length. Now, if we have a parallelogram, so a quadrilateral, opposite sides are parallel from each other, and all four sides are in fact equal, then we have a case called a rhombus. Okay, so a rhombus is a specialized case of a parallelogram, which is a specialized case of a quadrilateral. Okay, they could be right angles, in which case they'd be a square, so it's a special case again. But a rhombus, just notice that these are parallel and these are parallel, and beyond that, all of them have equal lengths. Okay. Finally, something that's probably a little more familiar, a rectangle. So a rectangle is also a parallelogram, but the angles are all right angles. So remember that this side and this side are parallel to each other. These sides are parallel to each other, and that also means that this side and this side are equal length, and this side are also equal length. Specialized case there is a square. Everybody's worked with squares before. A square is just a rectangle and it has four equal sides. So we still have those right angles here, and we have equal length on the sides. Okay. Now, beyond quadrilaterals and triangles, we have lots of other potential shapes. A pentagon is a five-sided polygon. Penta means five. And so you have a five-sided polygon. It does not have to look like the literal pentagon in DC, okay, like this one does here. You could have it be any shape, really, as long as it has five sides. Let's see if I can just draw one off the cuff. You could have that as a pentagon because there's 1, 2, 3, 4, 5 sides. A hexagon, hex means 6, is a 6-sided polygon. Okay, again, it doesn't have to be this pretty. Any polygon that has 6 sides is a hexagon. And everybody's familiar with the octagon. It's an 8-sided polygon. What do we always think about with an octagon? We always think of our stop sign. Octa means 8. That's where octagon comes from. Okay, now a circle is different than a polygon where it's connected by all of these different line segments, okay? A circle is just a set of points that are the same distance from some other point, which is called the center. So what you're talking about is you have your center here, and all of these points out here are the same distance away. Specifically, the distance that they are away is called our radius. Okay, so the point from the center is the radius. It's a line segment from that center to any point on the circle. And the diameter is a line that goes through the center and is straight across the circle. So any line that goes across the circle and goes through, has to go through that center, it is considered a diameter. Now, a diameter is 2 radii, okay? So 2 times your radius is going to give you the diameter, okay? Because this is a radius too, okay? So 2 of those would give you all the way across with the diameter. Something that is important is that this is not a diameter, okay? Because it did not go through the center. Now, if we're going to talk about 3D figures, we can talk about prisms. And a prism is just a 3D figure whose top and bottom are the same. And they are parallel to each other. So you have to think about a plane, not just a line, okay? So this triangle right here and this triangle right here are parallel to each other. If you had pieces of paper, they would be stacked on top of each other. If you think about the floor for your 3rd floor and the floor for your 2nd floor, they are going to be parallel to each other. So that means that the edges have to be parallel because they're not going to touch. So these, this, and this are parallel, as are this, and so on. A cylinder is similar to a prism, but we have circles as our top and as our bottom, okay? They are going to be parallel, again, just like 2 pieces of paper or the floor and ceiling. And then they are connected kind of by, you know, that soup can idea, okay? A lot of times we think about this as a soup can. Sometimes we can think about this as a wedge, or some of my students think about it as a piece of cake, okay? Now, a sphere is just a 3D ball, okay? It's a 3D circle. So you can think about beach balls, basketballs, whatever, a marble. It still has a center in here, and it still has that diameter and that radius. But now we're talking about all points in 3-dimensional space around that center, not just the 2-dimensional space. So instead of a cutout of a circle on a 2-dimensional piece of paper, you're now talking about a ball. Now, going back to polygons, we can talk about several different ways to label them. So similar to the way that we were naming the angles earlier, we can use the names of vertices to label a polygon. So it's really easy to name a polygon, okay? Just pick a starting point. Here, makes most sense to start with A, right? Most of us, if we were asked to label it, would just say, okay, I'm going to name it A, okay? You have to go in one direction. So you can go clockwise or you can go counterclockwise. It doesn't matter, but you have to go in order. So here we could name it A, B, C, D, E. Or we could have gone the other way and named it A, E, D, C, B. Or we could have started with something else. We could start with D. D, C, B, A, E, and so on, okay? The point is, pick a starting point and go around in a circle from there, either direction. Don't skip around. It could not be, let's see, A, B, E, C, D. Because in that case, we're skipping around, okay? Remember that we can't skip. Now the sides we refer to by their line segments. So here, where is side AB? This is going to be side AB, because this line segment goes from A to B. Now I've already hit on this a little bit, but remember that you can name an angle by 3 points. Point on one ray, the vertex, and then a point on the other ray. But as long as there's no chance of misunderstanding, you can name an angle just with its vertex, okay? So in that earlier polygon right here, you could name angle A is very clearly this angle. There's no other angle it could be. Angle C is very clearly this angle. There's no other angle it could be. They could just as easily be angle BCD or DCB or EAB or BAE, whatever. All of those are equivalent for their respective angles, but you can, in fact, just use one letter, and our text often does that. Again, remember, if you use the 3-letter system, your vertex must be the middle letter. Let's look at an example here. We want to first find angle AKB. So to do that, we're going to find point A, we're going to find point K, and we're going to find point B. And we just want to connect the dots in that order. So we go from A to K and K to B. It's that angle right there. If we want to name an acute angle, there's lots of them here. Okay, lots of small angles. We could name angle CKD. We could name angle AKE, and so on. Just remember, it has to be less than 90 degrees. So it's not either of these two right angles, okay? For an obtuse angle, there's a lot of options here too. We could say angle EKC. We could say angle, let's see, CKE. We already named that one, I guess. We could do angle BKE. And so on. There's a lot of them to choose from here. And for the right angles, remember, we're looking for this symbol here. So we have angle AKB or angle BKC. Now remember, you could name those in opposite order, but remember that K has to be in the middle of them. Okay, same with all of those. We could not here say angle K, because there are a lot of angles that we could be talking about that have K as a vertex. We just listed all of those. So make sure that you use the 3-letter naming system anytime that there's that ambiguity, okay? Now we're going to talk more about triangles in the next section, like a lot about triangles. That's all the next section's about. But let's talk about a brief overview now to kind of get us started. All angles in a triangle have to add up to be 180 degrees, okay? So if you have, on your test, you will have one of these, a triangle where you have different labeled angles, and you know that they have to all add up to be 180 degrees, and you want to solve for X, well, you just need to add them up to 180, okay? So here we would say, well, we know that 180 has to be the sum of X plus 2X plus 3X. So that gives us that 180 equals 6X. If we divide 180 by 6, we see that 30 equals X. So X must be 30 degrees. Okay. We can verify that by saying, okay, well, X would be 30. 2X would be 2 times 30, which is 60. And 3x would be 3 times 30, which is 90. If we add that up, 30 plus 60 plus 90 is going to equal 180 degrees. So we are good. If you lost me there, make sure you pause, rewind, do what you need to do, because you will see these again. Now, if we want to measure an angle in the real world, we often need to use what is called a protractor. And we are not going to do that in this class, as far as me handing you a protractor and asking you to measure. However, I will show you graphics like this. So a protractor is going to measure from right to left. So what that means is you're going to put this dot right here on your vertex, and you want to put this part on that straight line, and then you want to see where this line goes. Now be careful on this protractor. Notice there's two sets of numbers. We are counting from 0 to 180. So we want to use this first set of numbers when we are measuring. Okay, so here we see that our line goes through right here. So it is going to be 30 degrees. Be careful, it is not 150 degrees. And how could you tell that? Well, first of all, remember we're going to measure from 0 to 180 this way, okay, counterclockwise. But also, you should see a red flag, and this is obviously an acute angle. It can't be 150 because it has to be less than 90, okay? Now, just as a fun fact for you, any polygon can be split into n-2 triangles. So if you have an n-sided polygon, you must split it up. You can carefully draw n-2 triangles, okay? That has a helpful ending result, that the number of degrees in any n-sided polygon has to be 180 times that number of sides minus 2, okay? We're going to use that here in a few minutes for an example. So if we have a 4-sided polygon, so this polygon right here, we can draw that into n-2 triangles. So 4 minus 2 equals 2. And sure enough, here's one triangle, here's 2. 5 sides, 5 minus 2 is going to be 3. So you have one triangle here, 2, 3, and so on. Now, if we have two polygons that have exactly the same shape, we say that they are similar, okay? Now, that does not mean that they have to be the same size. We just mean exactly the same shape. And we'll talk about this with triangles in the next section. But we could have this triangle, and we could have this triangle, okay? And they might be what we call similar. They're the exact same shape, but they are not the same size, okay? What makes them similar is that all of the angles are equal to the angles in another polygon, okay? So each of the angles have corresponding angles. How do we know if angles are equal? Well, most of the time we're going to see the angles marked with arcs. And arcs are just these little curls right here. So this angle and this angle, they both have a single arch. So that means that they are going to be similar, or they are going to be congruent, okay? That means that this angle measurement is equal to this angle measurement, okay? Sometimes you can see other notation, like an angle with a little line through it, or a little arc with a little line through it. You're looking for same symbols, okay? As long as the angle is marked with the same symbol as another one, they are going to be equal, okay? Sometimes it says seeing one arc, you might see 2 or 3 or more than that, okay? Again, same symbols, 2 here, 2 here. Okay, let's get some practice before we wrap up this section. This is a great place. We've talked about a lot. I've thrown a lot of words, a lot of vocabulary, and probably dug out a lot of cobwebs from your brain. So take a break if you need. I'm going to work through these problems, but I highly encourage you, as always, to pause and work through them on your own. If you need to watch my solution to get yourself jump-started, that's fine. But make sure as you study and as you prepare that you can go back and do it entirely on your own from a blank piece of paper. That is going to help you prepare for the test. Okay. Suppose angle ABD measures 120 degrees. What is the measure of angle CBD? Well, this tells us the angle ABD, this whole thing, is 120 degrees. And we want to know CBD, okay? So we want to know what this one is, okay? Well, how do we tell that? Well, you should see this angle right here, so that means that is 90. So if the whole thing is 120, then the only thing left can be 30 degrees, okay? 30 plus 90 is going to give us that whole of 120. We want to find each angle of the triangle here. Now be careful, this is a common mistake on homework, on tests, on lots of things, okay? Read the question, it's asking us for each angle. We need to solve for X first, but then we also need to talk about each angle, okay? Now remember that the angles of a triangle add up to be 180 degrees. So that means that we know that 3x plus x plus 15 plus x minus 10 has to be 180. If we combine like terms, we see that we have 5x plus 5 equals 180, which tells us that 5x equals 175, which tells us that x, if we use our calculator, is going to be 35. We are not done, okay? 3x is 3 times 35, which is going to be, I believe, 105, but let me check. Right, so this is going to be 105 degrees, okay? X plus 15 is going to be 35 plus 15, which is going to give us 50 degrees. And x minus 10 is going to be 35 degrees minus 10, which is going to give us 25 degrees, okay? Now we should always check ourselves here, okay? Is 105 plus 50 plus 25, what does that equal? 105 plus 50 is 155, plus 25 is in fact 180. So we are good to go. It is always advisable to check your answers here. Okay. Oh, excuse me, sorry. Another one. We're gonna get lots of practice here. Two angles in geometry are said to be complementary if the sum of their measures is 90 degrees. Okay, so if one angle is 35 degrees, what is the measure of the other one? Well, we know that they have to sum to 90. So we know that some angle plus 35 has to be 90. So the missing one will have to be 55 degrees. And you can check yourself. 55 plus 35 is in fact 90, which is that complementary rule. Now let's talk about naming polygons, okay? What type of polygons do we have here? As always, please pause. I would really encourage you to pause here. Try it yourself. Here we have 1, 2, 3, 4, 5 sides. So we have a pentagon. Here we have 1, 2, 3, 4 sides. Nothing is parallel here, okay? It looks kind of close, but they're definitely not. So really all I would say here is a quadrilateral. It's possible that you have a set of parallel, but they're not marked. So we're just going to say quadrilateral. Here we have 1, 2, 3. So we have a triangle. Again, nothing's marked, so we don't want to talk about any special type. Here we have 1, 2, 3, 4, 5, 6, 7, 8 sides. So it doesn't look anything like a stop sign, but it is in fact an octagon. Okay. Now let's keep in mind that the sum of measures and of angles in any polygon, remember, thanks to that triangle, you can split into n minus 2 triangles. The total angles is going to be 180 times n minus 2. Okay. So what would be the sum of measures of the angles in a hexagon? Well, this is two parts. In hexagon, how many sides do we have? Well, we have n equals 6 sides. So that means that we're going to have 180 times 6 minus 2, which if we put that into our calculator, we are going to get, let's skip the page here, 720. So 180 times 4 is going to give us 720. Similarly, what is the sum of the measures in a quadrilateral? You may know this already, but let's look at it with this formula. In a quadrilateral, we have n equals 4. And so we have 180 times 4 minus 2, which is going to give us 360 degrees. Okay. If all 5 angles of a pentagon are equal, then what must be the size of each angle? So this is going to put together a little bit of everything that we've just learned. So we have 5 angles, and we know that they're equal. So we know that 5 times whatever angle equals something. What must it equal? Well, in a pentagon, we have n equals 5. So the total degrees must be 5 minus 2 times that 180, okay? Because of that 180 times n minus 2 rule, okay? I put them in opposite order, but that doesn't matter. It's going to be 3 times 180, so that's going to give us 540 degrees total. So that means that 5 times the angle have to give us 540. If we do this here, we're going to get that x has to be 108. So each of the 5 angles has to be 108 degrees. And you can check yourself. X plus x plus x plus x plus x 5 times is going to give us that 540. That's the total angles. Okay, let's move to talk a little bit about circles. Find the diameter of a circle whose radius is 15 centimeters. Okay. So we have a circle, and we know that the radius is 15 centimeters. Remember, the diameter is all the way across. So what does that give us? Also, remember that the diameter is 2 times your radius. This is a good time to point out that you will still have the formula sheet for your test. I will be sure to give you all of the Unit 4 formulas for this one, obviously, because we're doing Unit 4. So go ahead and start looking at that and make sure that you know what is and isn't given. You don't need to devote brain power to memorizing stuff that's given to you on the test. Make sure that you know where to find that information and how to use it, and that's how you'll succeed. If our diameter is 2 times our radius, that means it's going to be 2 times 15 centimeters. So that means our diameter is going to be 30 centimeters. Okay, let's say that we have a round pizza and we're cutting it into 12 equal pieces. Okay, so I'm not very good at this. I'll just go ahead and warn you. Hopefully I end up drawing 12 this time. Let's see, 1, 2, 3, 4, 5, 6. Yeah. Okay, so we have a piece of pizza or a pizza like this. Hopefully they cut it better than I just did. Okay. And it's 12 equal pieces, and we want to know the size of the angle of every one. Now they're equal, so pick any angle, and that's going to be what we want to measure. The key here is that you have 12 pieces. So you're going to take your total degrees for a circle, and you're going to divide it among those 12. If you think back, the total degrees for a circle, if we're going all the way around, is going to be 360 degrees. If we take 360 degrees and divide it by 12, that means that each piece has a 30-degree angle. Okay? You need to take a break, do so. We're near the end though, and you can power through. Two angles are said to be supplementary. Remember, we had complementary earlier that they added up to be 90, but now we're going to say they're supplementary if their sum comes to 180 degrees. If two angles are equal, what is the measure of the angle? Well, we know that they are equal. So the angle of the first one plus the angle of the second one is, each of them are equal, okay? Have to be equal to 180. So 2x equals 180. And so x is going to be 90. Okay, 90 plus 90 is going to be 180. Several ways to think about this. Supplementary angles have to form a line. So this angle and this angle. And if they're equal, you're going to have to cut it in half. And you can see pretty easily that those are going to be right angles also. So however you want to think of that, algebraically or graphically. Let's practice reading the protractor. Take a moment and pause and tell me what you think. Now remember here that we're going to measure up this way, and we're going to use this first set of numbers, and we see that it is going to be right here, which is going to be right around 75 degrees. Remember to use this set of numbers, okay? The ones that are between these two lines, okay? Not these, okay? Or we're measuring on the inside. We have about 75 degrees here. It would not be 105 because we see that it's not obtuse. So kind of use all your tools in your toolbox there to make sure you don't make a mistake. That was a lot of talking at you, I feel like. Definitely go back, re-listen, rewind, take notes, do what you need to do. Hopefully you've read your text also. Get lots and lots of practice, okay? Geometry is going to be all about practice. And this unit can be really fun and fairly simple for a lot of students if you practice. It might be confusing at first, but a lot of students get it after practice, okay? If you have questions, remember you can reach out to me. You can reach out to the Math Lab. You can reach out, make sure that you're taking a look at all the resources available to you in Blackboard, the other lectures, the other notes. Definitely get all that practice in your text, okay? A lot of what we've seen today is definitions, but don't let that fool you. Those definitions are going to play a part in the problems that you are given. If you don't know what the problem's asking, you're not going to be able to answer it, okay? Thanks for tuning in as always, and I hope to see you guys next time.